Okay, so we're gonna quickly go over a few of the things that you'd seen in the reading that we went over. First of all, the important thing you need to know is radioactivity is an attempt. It's a way that an atom, specifically a nucleus of an atom, can get to a more stable form. So when we talk about radioactive elements, a lot of times these are really big elements. They're big atoms, right? So they have many, many particles, and they're unstable because there are so many particles. The three types of radioactivity we're going to focus on are alpha, beta, and gamma. And they have the little, these are just Greek letters. They're the first three Greek letters. And that's the order that they were discovered in, I believe. So alpha, beta, gamma. And they're indicated like with those symbols. Okay, I'm going to be using nuclear notation. So the way nuclear notation works is you have an elemental symbol here. And then up in the top, this is the mass number. The mass number is the total number of nucleons. That's protons and neutrons added together. So again, we're only talking about the nucleus. Electrons are not really going to be part of it. You'll see an electron in a beta decay, but it's not. We're not concerned with that electron we're not concerned with electrons outside the nucleus. And then finally, this is the atomic number, which is the number of protons. And this is important because the number of protons defines what element an atom is, right? So if we look at the periodic table, you'll see carbon is the sixth element. That's because any atom, any nucleus that has 6 protons is carbon by definition. But there are many forms of carbon, right? You can have carbon-12, which is a relatively stable form of carbon. That would be 12 up here. So, you know, if I was going to write that out, I can write that out for you. Right, so if I'm going to have carbon, right, the way I could write this out, I don't know what's going on in this pen. It works and then it doesn't work, so I'm sorry. All right. I guess I'm just not pushing down hard enough, which is kind of annoying. Anyways, so there's C, which is the symbol for carbon. And then up here, this is not going to be good. I'm just going to have to draw with the mouse, which means it'll look crappy, but I can't do anything else about it. Okay, so this would be carbon-12. 12 nucleons, so that's 6 protons, obviously, because that's what makes it carbon. And the other amount, so if you take 12 and subtract 6, you have 6 left. That would be 6 neutrons. The type we oftentimes are talking about is carbon. When we talk about carbon radiometric dating, is carbon-14. Now, the number down here still has to be 6, of course, because that defines it as carbon. So how many neutrons are here? Well, if you took 14 minus 6, we would see there are 8 neutrons in this carbon atom. So this is unstable, right? This undergoes what we call beta decay, and we'll look at it later, but this is unstable. But the point is, these are both types of carbon. And so these are called, they're obviously different, so they're called isotopes. An isotope is, these are isotopes of carbon. An isotope are the same element or the same number of protons, but they might have different number of neutrons. Theoretically, you could have any kind of isotope you want, right? You could have carbon-13, where there are just 7 neutrons. You could have carbon-28, where there would be 22 neutrons, and so on, right? So theoretically, now that would probably not be very stable, and I don't even know if we could synthesize something like that. But carbon-14 is a naturally occurring isotope of carbon, and carbon-12 is a naturally occurring isotope of carbon. Carbon-12 is stable, carbon-14 is not. And so eventually it will decay into nitrogen-14 by beta decay. So we can often figure out the information, like we can figure out the number of neutrons simply by taking the total mass number, which is the total number of nucleons, protons, and neutrons, and subtracting the number of protons. All right, we're going to skip that. You can definitely watch that video if you'd like later. It's good. The first type of decay is alpha decay. So again, you've already looked at this. So we talked about how this is the weakest type. But let's look at an example of an alpha decay. So the alpha particle is emitted. The alpha particle is 2 protons and 2 neutrons. See there, 2 protons, 2 neutrons. When this is written out, it's often written out like this right here, a helium nucleus is what it's written as helium, because if it has 2 protons, it's helium. So helium is emitted by this. Now, actually, as you probably know, helium is not, it's hard to contain helium on Earth because it escapes Earth, right? If you have a helium balloon, you know this. The balloon gets lifted up way into the atmosphere, and although the balloon eventually pops, the helium literally leaves Earth and goes into space. It's too light for Earth to hold on to. So the only way we have helium is because helium, there's uranium in Earth's crust, there's uranium in Earth, and it undergoes this process, and that helium that gets emitted gets trapped, basically. So helium is produced inside of Earth and can get trapped in pockets of Earth. So you may hear about like a scarcity of helium. It's not exactly true. There is still a lot of helium available, but it is true that helium is kind of a non-renewable resource currently. We have to wait over time to have helium produced naturally. Anyway, so you have a helium nucleus here, and then the remainder has to go over here. So you'll notice that it's an equation. It basically all works out. 238. If you add those two together, you get 238. So since 4 particles left, 4 nucleons left, there are only 234 nucleons left here. For the bottom, there are 2 protons that left, so this gets subtracted by 2, so it balances out. And since it has a different number of protons, it is now a different element. It's thorium. And again, you can just look this up on periodic table. You pull up periodic table, and thorium is going to be element number 90. Let's look at an example together. Oh, see, here's thorium. I'm going to pull up mine so I can write. There we go. Okay, this is alpha decay example. Neptunium has an atomic number 93, an atomic mass of 237. An atom of Neptunium-237 undergoes an alpha decay. Write out this process using nuclear notation. All right, so again, I'm going to have to write with my mouse, so it'll be a little sloppy, unfortunately. All right, so we're going to write this out. This is what it'll look like. Over here, we have Neptunium MP. The atomic mass goes up here, 237. And the atomic number is 93. It's going to undergo an alpha decay. So what I'm going to do is I'm going to go ahead and put my alpha particle here. So again, if you reference your notes, you should see it there. Or if you look back on this previous slide, you can look at it there. But the alpha particle is 4 nucleons, 2 protons, and 2 neutrons. So the number of protons will go down here. And again, this is a helium nucleus, is how we write it, notate it. So this is the alpha particle. Plus, now we figure out what's left over. So this is where it literally is just like a simple math problem, right? Because we just subtract. So on top, we had 237 minus 4 gives me 233. On the bottom, we had 93 minus 2 gives me 91. So now I need to figure out what element this is, what atom this is. And I can do that by simply looking up number 91 on the periodic table. So I'm going to do that. Obviously, you could pull up periodic table if you need to there. All right, so I'm looking for 91 here. I know it's a little small. I think if I try to zoom in, though, it won't quite zoom in correctly. So if you don't know, by the way, this green part here, it literally fits in between here. So the entire periodic table is obviously very wide, so they often break it down by putting the lanthanoids and the actinoids down here. Okay, what did I say, 90 or 91? Uh, 91, okay. So element number 91 is protactinium. Great, PA, that's the symbol I need. Okay, so I'm going to put that down. PA. And there we go. Right now our alpha decay. Neptunium emits an alpha particle, and the new element, the new nucleus left, is proactinium-233. Now, it's not guaranteed that this is a necessarily more stable form. This might be another intermediate where it will go on to something, but it will eventually get to a more stable atom, as we'll see in just a minute. Okay, let's go on to beta decay. As I kind of talked about earlier, or yesterday, you can think of a neutrino obviously neutron has obviously zero charge. So you can think of it as a proton and electron kind of together, right? Because their charge would be -1 plus 1 would be 0. The masses don't quite work out, so there's another particle here called the positron neutrino. But the point is, when we write out a beta particle, it usually looks like this right here. It's usually E. E and then a -1 down here because it has no nucleon, but it's a negative charge basically. So in beta decay, you'll notice the mass number doesn't change. It's 231 before, it's still 231 after. What does change is the number of protons, basically increase of protons. So the proton gets left behind, the electron gets emitted from the nucleus, and it has gained 1 proton. So it lost a neutron, gained a proton, which is why nothing changes up here. Lost a proton, lost a neutron, gained a proton, but you do gain 1 proton, so that's 92 on the bottom. We'll look at an example. Okay, an atom of americium-245. This is an element named after America. There are a lot of elements named after places. A lot of times they're named after the place where they were discovered. So I'm going to go a beta decay route this decay using nuclear notation. So americium, AM. I put capital M. It should be lowercase m though. All elemental symbols are a capital letter followed by undercase if there are 2 letters there. Okay, americium-245 goes up here because that's the atomic mass. And it says the atomic number is 95 down here. It's going to go beta decay. So as I previously said, for a beta particle, there's no change in it is not a proton or neutron, so 0 there. And it has -1, it's -1 protons. Basically, it's a negative charge. So as long as you get that symbol down, then again, it's just like a math problem. On top, it's 245. On the bottom, 95. And over here, it's -1. So if -1 plus x equals 95 is the way you can think of it, the answer should be 96 down here. 96. So now I need to look up and see what is element number 96. Again, if you happen to have the periodic table memorized, it would help. I don't, but if you did. 96 is curium. There you go, named after Marie Curie. Curium, so 96 is CM for curium. So I need to go back to my CM. So there you go. Americium-245, it undergoes beta decay and turns into curium-245. The atomic mass is preserved, but the atomic number changes. And that's what happens to carbon-14. Again, that's a very common... So as you can see, right, like, we can write this out, and it's important to know how to... I think it's good to know how to write this out. But obviously, the net changes, it just kind of goes up 1 on the periodic table, right? It went from here to there. Well, the same thing happens with carbon-14. Carbon-14 undergoes a beta decay, turns into nitrogen-14. Which is ostensibly more stable. In fact, you can kind of tell, this isn't too important, but nitrogen-14 seems stable, I think, because for the lighter elements, it's almost, you want equal numbers of neutrons and protons. So nitrogen-14 has 7 protons and 7 neutrons. That would be pretty balanced, and that would work out really well. Okay. There's one more thing I want to show you. Oh, gamma. Obviously, we're going to discuss it real fast, but we're not really going to write this one out because nothing changes, right? The energy, the state of the nucleus changes, right? But the actual composition doesn't change. So this is the highest energy. And if you really want to write it out, you can see how it's written out here as gamma emission. It's like 0 and 0 because nothing really changes. They just have this little symbol to show it's an excited state and it's an unexcited state. Or ground state is sometimes what we call it. Last thing I want to show you here is that this is uranium. So there are oftentimes chains of, there are these large chains of atomic or radioactive processes that occur. So you'll notice, like, you can write this out. This little chart here shows mass number, atomic number. So this would represent a alpha decay. So uranium alpha decays into this thorium. Thorium undergoes a beta decay into, I believe that was proactinium. Proactinium beta decays into another uranium. Again, these would not be the same though. They're different isotopes. I don't have the. Oh, you can kind of see. I mean, you could tell they could guess like this uranium-238. I'm pretty sure this is uranium-235. Then you have alpha decay, alpha decay, alpha decay, all the way down to lead, and then anyways, you end up at lead eventually. And these are different. These have different half-lives. So again, you can see here some half-lives. You know, different isotopes can have drastically different half-lives, right? So for cesium 135 has a half-life of 2.3 million years, whereas cesium 138 has a half-life of 32.2 minutes. So incredibly different levels of stability simply on the number of neutrons that are there. And this has to do with the atomic and the nuclear force that's inside of these nuclei. Again, here's radium. Once again, you can see pretty different. 1,600 years to up to, there's some that are a couple days. And there's some, like, for example, I think francium is the rarest element because I think it's most stable. Its most stable form has a half-life of something like 20 minutes, and that's its most stable form. I think it's estimated the total amount of francium on Earth at any given time is something is less than 20 grams or so. It's pretty amazing. Okay, there are again other videos you can look at. These are just some common half-lives. We're not going to do too much of the half-life math. It's not too bad really. It just has to do with a lot of like natural log, but we just simply don't have time for it. So we already discussed this carbon dating, but again, there's a video there if you want extra information. All right. So there's an assignment on Schoology. Should be pretty straightforward. I'll be happy to help you, but basically. It goes over radioactivity and specifically doing a couple of those types of equations where you write it out and show what it changes into. So you want to go ahead and start on that. And if you have any questions, please let me know.